So our first presentation is from Paul Hargrove. Paul is a computer systems engineer at Lawrence Berkeley National Lab, and he's been doing research on programming models and communication libraries for high performance networks since way before it was cool. So Paul, take it away.
Thank you. Hello, and welcome to an introduction to GASNet-EX for CHIUW users. My name is Paul Hargrove, and this is joint work with my colleague, Dan Bonacea. Oh, great. Now the slides aren't advancing. There we go. First, a bit about who we are. Dan and I work at the Pagoda Project at Lawrence Berkeley National Lab, where we focus on lightweight communication for exascale. This diagram shows our ecosystem. It's built on a foundation of GASNet-EX, the subject of today's talk. GASNet-EX is middleware providing a network-independent interface for implementing partitioned global address space, PGAS, programming models. So above GASNet-EX in the diagram are such programming models as CHIUW, Legion, UPC, and our own UPC++, among others. Above those are things like our CUDA, FlexFlow, and ultimately the applications of interest to our funding agents. Now onto some background and history. What is GASNet? Literally, it's an acronym for Global Address Space Networking. Practically, it's an API and its implementation featuring active messages, AM for short, and remote memory access, RMA. Its interfaces have been designed for use as compiler target and for authors of low-level runtime libraries. On most systems, GASNet is interoperable with MPI and performs as well or better than MPI. Additionally, GASNet has influenced the design of the RMA interfaces in MPI 3 and later. Last and certainly not least, GASNet is the recommended backend for CHIUW multi-locale communication on non-Cray systems, such as Summit, which is the second fastest system in the US, according to the most recent top 500 list. It therefore appears in the third-party GASNet directory of the CHIUW sources. So I've mentioned PGAS more than once now, so for those who may not be familiar, partitioned global address space is a paradigm for programming models in which there's support for global memory, typically designed to leverage the remote direct memory access, RDMA capabilities found in nearly all modern HPC relevant networks. Such models distinguish private from shared memory, separate synchronization from data movement in contrast to their coupling and message passing. They're both languages and libraries that provide PGAS. Languages include CHIUW, UPC, the Cray feature in Fortran 2008 and later, among others. Libraries include our own UPC++, OpenSHMEM, Cray C++, and others. What they all have in common is a semantic support for one-sided RMA. So here's what the basic idea of one-sided RMA looks like in PGAS models. A program has use of abstractions that allow a process to directly access the shared memory of another process without an explicit involvement by that other process. For two-sided messaging to deliver a payload into memory requires posting of a receive and matching of that receive to a send. Only once those two steps are complete can the payload data transfer be delivered. This is depicted by the crooked path in the upper half of this cartoon. In the case of a one-sided put, however, the destination address has been provided by the initiator, allowing modern RDMA-capable network hardware to deliver the payload directly to its final destination without any involvement by the target process. The nice smooth path through the lower half of the cartoon shows this case. The net result can look to the programmer like shared memory, but it can be implemented in distributed memory hardware. So GASNet-1 started in 2002 with the goal of providing a single portable communication runtime for three then current PGAS languages, UPC, Titanium, and Rice's dialect of Cray Fortran. As I mentioned before, the primary API features were RMA, one-sided put and get, and active messages, a restricted form of remote procedure call. We chose to implement our own library rather than adopting an existing one for reasons that are well beyond the scope of this presentation. Since the project began in 2002, GASNet has been both widely adopted and widely ported. Clients have included multiple implementations of UPC and Fortran Crays, the first OpenSHMEM reference implementation, and now more recent programming models such as UPC++, CHIUW, and Legion, among several others. Over the past 20 years, we've ported to probably every network relevant to HPC in the US, though many have since passed on. The current ones are highlighted here in bold. We've also supported over 10 compiler families, 15 operating systems, and dozens of architectures, though again, many of these are no longer with us. But wait, you may say, you mentioned EX. You've not mentioned EX since the first slide. Well, GASNet-EX is the next generation of GASNet. It began in 2017 with funding from the Department of Energy's Exascale Computing Project, ECP for short. And this work is motivated by changes in the programming models and the systems, both having changed significantly in the 15 years between 2002 and 2017. We're targeting the needs of newer pre-GAS programming models by applying now 20 years of lessons learned. We're retaining compatibility for the many GASNet-1 clients on the previous slide. Some of our motivating goals include support for greater asynchrony in the client, better client adaptation, such as the network congestion, reducing our memory footprint, improving threading support, supporting offload to network hardware, such as atomic operations and collectives, and support for RMA operations and device memory, GPUs in particular. So while this is not a tutorial, I'd like to provide a little bit of overview of what GASNet-EX provides. Continue with the basics from GASNet-1, active messages and remote memory access. AM is a restricted but powerful form of remote procedure call. CHIUW uses AM primarily for task launch. Our own UPC++ uses it to implement a more general form of RPC. Berkeley UPC uses it to implement remote memory allocation, and it can be used to implement customized rendezvous protocols, such as for a memory-constrained consumer. The RMA put and RMA get of GASNet-1 have been joined by atomic read, modify, write operations, such as fetch add. Like put and get, atomics are leveraging network hardware support where available, such as in the Aries NIC and the Cray-XC series. Much of our current work is on memory kinds, which is our term for the device memory support I mentioned a couple slides back. Memory kinds extends RMA to non-host memories. There are also two features in GASNet-EX, which were previously unofficial extensions to GASNet-1. We have a rich set of interfaces for non-contiguous RMA, which enable, for instance, movement of entire multidimensional array sections in a single operation with concise parameters. And finally, we have teams and collectives, where teams is our terminology for an ordered subset of a job's processes. Now onto the relationship between GASNet-EX and CHIUW. I did some archaeology in the CHIUW changes.md and Git repository history. And the oldest CHIUW release I could find record of was 0.4, released in December 2006, which clearly documented its capabilities, including single locale, multi-threaded. In July and November, respectively, of 2007, the 1.8 and 1.10 releases of GASNet were imported into the third-party directory of the CHIUW source repository. And later in March 2008, just 15 months after version 0.4, CHIUW 0.7 was released, documenting itself as the first version to claim multi-locale support. Reading the documentation of that release, you'll find that the instructions for multi-locale describe how to configure GASNet. And we've been happy collaborators ever since. So last week, I put Brad on the spot. Why did CHIUW choose GASNet? I won't read these all off to you, but these are some of the nice quotes that Brad shared with me. They echo many of the points I mentioned in earlier slides. Wide portability and wide adoption of GASNet, the utility of active messages, the performance of RMA, and design amenable to compiler-generated code, among others. How does CHIUW use GASNet today? Currently, the CHIUW runtime uses only the features that were available in GASNet-1, even though it embeds our current GASNet-EX releases. Active messages are used, as I mentioned, primarily for remote task launch, though there are a few internal bookkeeping things done with it as well. Contiguous RMA is used for one-sided efficient one-sided data movement, and non-contiguous RMA is used for moving around array sections. So I mentioned before that we've been collaborators since the early days of CHIUW, so I'd like to report briefly on two specific interactions from last year, both related to the CUDA ArcSort benchmark that Brad mentioned early this morning. If I'm not mistaken, this slide actually reports on work that was also featured in a presentation Elliot Runnihan made at last year's workshop. While running the CUDA ArcSort benchmark on an HP Apollo system, Elliot observed the performance anomaly shown by the lower green line. As the number of locales grew past 64, throughput was declining rather than increasing. Since this system features an InfiniBand network, GASNet-EX IBV conduit is used for communication. Working together, Elliot and I determined that the logic I wrote for dynamic memory registration in IBV conduit was, let's call it, out of date. By that, I mean that the parameters I built into the system when the code was originally written on 32-bit systems were simply not appropriate for modern nodes with 2 terabytes of memory each, let alone a couple hundred of them. So our collaboration led to a bit of a refresh of that stale code. And as the graph shows here, over a 10x performance improvement at 240 locales, as seen by the difference between the two series. Though to be honest, Elliot does say that some of that came from simultaneous improvements he made in the communication aggregation in CHIUW. A few months later, Elliot had another performance issue to share with me. I believe we're looking at the same system, same benchmark, but at a different problem size. The after code from the previous slide is now the before, so the lower green line. And while you don't see anything wrong in this figure, the observation that Elliot made was that as the number of cores used per locale was increased, the performance began to fall off. Elliot and I identified the root cause as a false sharing problem in Mellanox's libIB verbs. So I devised and Elliot validated a workaround in GASNet, which allowed productive use of the full 120 available cores per locale. And as you can see in this plot here, this yielded a 20% performance gain at the largest size, 240 locales, as seen as the difference between the two series. I mentioned performance, in particular as compared to MPI, as one of the original motivations for CHIUW's adoption of GASNet. So now I have some micro benchmark results to share with you. However, I want to note that these following slides have been extracted from other presentations with a much different focus, for instance, reviews of our program. So I'll be addressing only a portion of what's on each of these next few slides. This is RMA performance of OFI conduit in our latest release compared to MPI RMA and message passing on Crusher, an HPE Cray-EX system with a Slingshot 11 network. Crusher is a precursor to OLCF's Frontier, which is now #1 in the top 500. So we're hopeful that these results are representative of how we'll look on Frontier when we're able to get access. Comparing the performance of RMA puts, which are the solid lines with shades of blue, one can see that GASNet-EX and MPI reach the same peak bandwidth, but that we reach it 4x sooner, with 16 kilobyte transfers versus 64 kilobytes. Looking at RMA gets, which are the dot dash lines in shades of red, we see that GASNet-EX reaches a peak which is 11% higher than that achieved by MPI. And my final observation on this slide is that all 4 RMA series outperformed message passing, MPI message passing being shown by the dashed green series. And this I take as confirmation that RMA and PGAS do represent a better semantic match to the capabilities of modern hardware, network hardware. Here's some similar results comparing GASNet-EX RMA to performance of MPI across a variety of systems. The upper left line plot is the same data as the previous slide, but without the annotations. The upper right is Nurse Perlmutter. This is another HPE Cray-EX system, but this one with a Slingshot 10 network. Lower left is OLCF Summit, an IBM Power 9 with dual rail InfiniBand network. And finally, the lower right line plot is from Nurse Corey Phase 1, Cray-XC with the Aries network. Well, the details differ a bit. There are 2 observations which apply uniformly. GASNet-EX RMA meets or beats MPI RMA consistently. And with small exceptions, message passing is almost always underperforming RMA on all systems. I previously mentioned memory kinds. I work to extend RMA support to non-host memory. This slide shows the performance implications of that work for a UP C++-based micro benchmark performing gets from a remote GPU to local host memory on OLCF Summit. The lower series with open blow circles is the before. Without support in GASNet-EX for RMA to or from GPU memory, the UPC++ runtime was performing a host-mediated copy. This means that a use of a CUDA mem copy or similar staged memory from the GPU to the host memory, and then the actual RMA operation was issued with the InfiniBand NIC using the host memory. This little dance is depicted in the left half of the cartoon along the top of the slide. The alternative is shown in the right half of the cartoon. In the case of NVIDIA GPUs and Summit, GASNet Memory Kinds is now utilizing a technology known as GPU Direct RDMA, GDR for short. This is a marketing term for PCI peer-to-peer transfers. As the cartoon shows, in the right half, this allows the data stream from the GPU through the chipset to the network without involving the host memory or the host CPU. The upper series on the graph with the red filled circles shows the performance of the same UPC++ benchmark utilizing this technology once it was added to GASNet-EX in the form of memory kinds. The result is a 2x performance improvement for large transfers and a 30x improvement for small transfers. For reference, an analogous benchmark of CUDA-aware IBM Spectrum MPI is shown by the middle series with green X's. Switching things up a bit now, we're looking at a different network, now the HP Slingshot 10, and a different GPU vendor, now AMD. This is the same UPC++ benchmark code, though now the transfer is a get from remote GPU to a local GPU, where previously it was into local host memory. As a result of the GPU vendor change, the PCI peer-to-peer transfer technology now goes under the name of ROCm RDMA, but the principle is the same and the results are surprisingly similar. 2x improvement for large transfers and 30x for small. Well, there's no MPI data in this plot. I've instead plotted the speed up as the blue line without markers to be read against the right-hand side. And as you can see, it ranges from 30 down to 2. So porting to the HP Slingshot networks and work on memory kinds represent our most recently completed work. What are the next steps? So the top priorities include extending memory kinds in 2 dimensions. We currently have memory kind support for 2 network APIs, IBV, that's the libIB verbs, and UCX, but not yet for OFI, for libfabric. Since that's a network API for the HP Slingshot 11, which in turn is in all of DOE's new exascale systems, providing support for that is our top priority at the moment. Next in importance is extending our support beyond NVIDIA and AMD GPUs to include Intel GPUs, which are to be the accelerators in ALCF's Aurora system. Finally, as I noted earlier, Chapel is not utilizing memory kinds or any other improvements in GASNet-EX. This is ironic since programming models like CHIUW were our motivation for GASNet-EX work in the first place. So we look forward to assisting the CHIUW developers in future efforts to embrace more of GASNet-EX than just the legacy GASNet-1 functionality. In particular, I want to make a reference back to Engine's mention that we need to work together to see how memory kinds can address their needs for GPU locales. I'd like to very quickly acknowledge our funding sponsor and the 2 centers where I collected the data presented. And of course, I'd like to thank you for your time and attention today. And I'll open the floor to questions.
And thank you, Paul. Yeah, any questions, please raise your hand, or you can unmute if you're very quick. We got a question from Brad.
Yeah, Paul, I had a kind of dual question, the one that Dan asked Engin earlier on. So Dan asked Engin, what are you going to do in terms of GPU transfers? And, one interpretation of Engin's answer might have been, well, we're just hoping GASNet will take care of that for us, which I think is reasonably accurate. Given that you know what GASNet does and does well and does poorly, probably, and how CHIUW's using GASNet and perhaps how we should be using it more, as you just alluded to, do you see storm clouds on the horizon there, or problems we should sort of be thinking about or aware of earlier on? Or do you feel like things are going to be in good shape and we're going to be able to benefit from a lot of the GPU work that you demonstrated in the context of UPC++ and things like that?
Right. So that sounds like the agenda for a 90-minute meeting, but I'll try to make the 90-word or 90-second version instead. So my main concern to address the storm clouds terminology used is that Engin talked about GPU initiation of communication and mentioned NVSHMEM, and that's not currently something we're targeting directly. I believe that the CHIUW runtime would likely need to provide the what do I call it? The thunk back to a CPU thread that would actually perform the injection. But the portability beyond the libIB verbs of NVSHMEM would certainly be something you would be able to leverage right away. And I think in the future, we will probably have to do something with GPU initiated communication. It's just not in our current funding scope. In terms of what we do and do well, I think you saw host memory, so from GPU to host memory, from GPU to GPU, and we do all the combinations, and I think we do them pretty well. What wasn't shown was the comparisons between host and GPU host, et cetera. And they all saturate pretty much the same wire speed. They are limited by chipset and switches and NICs rather than by the mediation that was the bottleneck, the copying to the host memory as a high latency issue. The 30x speed up for the small was due to that. I think fundamental to how that gets used in CHIUW is a better understanding of how data is staged. So if at the very beginning of a CHIUW application, the data is sort of generated into GPU memory and lives there forever, then we might eventually be utilized for things like ghost zone exchanges, whatever. But if there is more movement between host and GPU memories continuously throughout, then I think being able to do these asynchronously without tying up the GPU in the CUDA mem copy type data movement operations, things like that, are definitely something that we can engineer good solutions to. But that's going to take, as I said, more of a 90-minute meeting than a 90-second answer.
Great. I appreciate the short answer and look forward to the longer meeting sometime.
And I would like to just amplify Paul's answer and say that the micro benchmarks that were shown on the earlier slides were all one-sided RMA for the most part in UPC++, where kind of the program, the micro benchmark has already arranged to know that this is a one-sided transfer, so you don't have to pay any cost to figure that out. But if the CHIUW runtime needs to do more work in order to get all that information onto the initiating process, then that will add some overhead. So part of this is going to be how you engineer your multi-locale support for GPUs in order to allow it to leverage RDMA whenever possible.
Okay, maybe time for one more quick question from Tom Westerhoff.
Yeah, I had a really simple one about the non-contiguous RMA. So could you perhaps tell a bit more like which patterns are supported? So say like strided to strided or strided to contiguous and all that.
Dan, why don't you take that one? That's your area.
Sure. So we have three different kind of flavors of non-contiguous transfers. We have strided, which is general n-dimensional array sections and transposes. We have vector, which looks like an IO vec, and then index, which is kind of halfway in between there where you're moving a list of elements. We don't specifically have support for strided to vector or, combining the two. If you're moving an array section, you're array section on both sides, but you can use the interface to pack and unpack during the transfer if that's what you're asking.
And certainly the strided can express a contiguous source or contiguous destination where the other side is not.
That's right. Yes. Did that answer the question?
Yeah, thank you. Thank you.
Okay, thanks again, Paul, and thanks, Dan, for also turning up to answer questions on your work.